Now that we've learned the Hilbert space for many-body quantum mechanics, and we've learned how to deal with operators, we've learned about occupation number notation and how to go into an efficient notation for calculating that and changing basis, all that's left is to actually do some useful calculations. Now, any interesting quantity we might want to know will always turn out to be embedded in an expectation value of something. So if we know every expectation value of every operator, then we know every physical quantity we can possibly measure. And because every operator can be written in terms of creation and annihilation operators, we'll always be trying to calculate some kind of expectation value of creation and annihilation operators. The nice thing about an expectation value is it's just a complex number. And so if I wanted to calculate these things, all I'd need to do is calculate those complex numbers. Now in these cases, they're functions of continuous and discrete variables, and so they'll be complex valued functions. Now if I was very lucky, I might be able to calculate the dynamics of those things in some kind of closed form. So I might be trying to calculate, for example, the time derivative of one of these expectation values. And you do that by taking the Hamiltonian for your system and taking the Heisenberg equation of motion for your operator and taking the expectation value of both sides. This is a typical kind of example. We've got the expectation value of this operator here. The Heisenberg equation of motion with the expectation values around gives you these terms. You've got kinetic energy terms producing those kinds of things. And you've got interactions between the particles causing that kind of term. Now the unfortunate thing about this, of course, is that these expectation values here are new quantities, and so you'd have to go and find how those evolve. And when you do that, you'll probably find there are more expectation values you have to learn, and so on and so forth. And if you're really lucky, that'll be a closed set. And what normally happens, of course, is that it's not a closed set. You have some infinite set of expectation values you have to calculate, and that becomes impossible. Certainly not without making approximations. So what approximations can you do? Well, maybe you don't have to make approximations. Maybe we can go down and calculate the whole thing properly. So maybe you can solve the actual Schrödinger equation for your quantum state, or maybe you can solve the Heisenberg equation of motion for your operators directly. And given a sufficiently simple system, this might be an analytic solution, in which case you'll be very happy. On the other hand, suppose there is no analytic solution. What are you going to do then? Well, how about a numerical solution? Well, let's think about just how big the size of this Hilbert space really is.